So this section, as you see here, is going to be about foundation design. The term foundation here is kind of large when it comes to definition. It includes lots of other items, here. So for example, when you look at a pad, you can call it a pad, which is one of this type of foundation, if you like. Also, you have mat foundation, which is extended in both directions, let's say the X and Y. And usually this mat foundation supports lots of columns. You have also D foundation, which is like piles foundation, like caissons. You have also a concrete slab. If you just put concrete slab on grade, you may also put foundation. So the term foundation here is really large. Just includes lots of items. The one that we are going to be working on is going to be this pad foundation. You can call it pad, or you can call it just foundation, a footing. You can also call it a footing. The one we are interested in is going to be supporting vertical loads and moments. When you have any column, and this column is like a frame column, this frame column is going to be supporting vertical load coming from the column itself. And in many cases, it supports a little bit of a moment coming from the column fixity to the footing itself. So we're going to be covering both of these two cases. It reminds me here with the column design that we have done. So in the column first, we say columns going to be exposed to vertical loads, and then later on, we start to add moment on the column. So after that, we decide that columns usually supports axial force and some moment on the top of it. Same thing with foundation, or with this footings or pads. Mainly, they are supporting vertical load. But in many cases, this pads or this footings, they support also a little bit of a moment coming from the fixity of the column to the footing itself. Here is one of the pictures that we have seen in the past from previous slides. And we say that this gives you our floor system or the concrete slab. Same thing, let's say for a couple of levels. And then you have this column here, which is continuous all the way to the foundation. So you have here a footing. This is what you call here a split footing, or we call it also a pad, or you can call it foundation if you want to. In some cases also we have this wall footings. So this wall footing is going to be extended. It is not just a piece like this. It does have a length and a width. It has a width and usually extended with the wall length. So what happens, load is going to be transferred through the column, goes all the way down, and then after that it's going to be supported by the footing, and the footing is going to be touching the soil. So this interface between the soil and the footing is going to be exposed to vertical stresses, because the load that you're talking here about, it is all about vertical loads, and again, some moment that comes on the top of it. So when you have the vertical load coming downwards, all the pressure is going to be acting upwards from the soil itself. So we have two main issues when it comes to design a foundation or footings. Number one is going to be the size of the footing in terms of length and width. In terms of length and width, now you start to think which one here is stronger. Is it the soil or the concrete? And of course, it's going to be the concrete. So we have an issue with the soil that we want to be sure that the soil allowable bearing pressure is still okay. So this allowable soil bearing pressure, we don't want to exceed when it comes to the applied pressure coming from the column. So based on this vertical load or axial load coming to the column, it's going to get transferred to the pad, and then from the pad to the soil. So the contact pressure between the footing and the soil is going to be equal to this vertical load divided by the area of the footing, or contact area between the footing and the soil. This contact pressure will be sure it's going to be within the allowable soil bearing pressure. Now, this allowable soil bearing pressure will depend on the type of soil. And as a structural engineer or concrete designer, You don't really come up with this value. Geotechnical engineer is going to give you this value. Geotechnical engineer is going to say the allowable soil bearing pressure for this soil at this location is going to be that much in terms of pound per square foot or kip per square foot in terms of PSF or KSF. Once you have this value, you're going to start to size the footing. What do you mean by size the footing? Come up with the length and width, and we're going to go through this in details. This is going to be the first item. And actually, this is not concrete member design. This is about sizing the pad, which means that you design the soil. The second item that you're going to be concerned about is going to be the thickness of the footing and the reinforcing inside it. This is here what we call concrete member design. So under this foundation, design slide set, we're going to be doing sizing of the pad itself, the concrete footing, which means the soil design. And the second item, we're going to be concerned about detailing and the amount of reinforcing that we're going to put into this pad. Is that okay? Here's another model, like 3D picture of a building. Again, this building is supported by columns, and the columns going to be taking the load, going all the way down to the footing. You can call it a split footing. And then the footing is going to be passed the pressure to the soil. Here's a building 3D web picture, and it shows a pavement. And as you see here, the column is going to be taking the load from the top levels. It's going to be going through here. So actually, the footing is going to be down here. It's going to be below the basement level. And you see it's going to be a footing here. You see this pad, it's going to be a pad right below the column. Now think about, again, the load path. Load is coming from the slab. It goes first to the beams. As you see here, it's going to be uniform load to the beams. And the beams here will be supported by columns, like these 4 columns. So you're going to have vertical pressure between the beam to the column. So this column here supports, again, axial load. And also, it could be also some moment that's not shown here. And then after this column is supported by this pad in the pavement. And then you see here the pressure below the footing itself. This is going to be the pressure that goes to the soil. In our structural design, we want to be sure that this column is able to support the stresses. And we have done this already by designing of the column. Now, after that, we're going to be taking this pressure to the pad, and then from the pad to the soil. Sizing the pad, which means length by width, is to control the soil pressure below this pad. And you want to be sure that it's going to be within the geotechnical report recommendations. Now, who's going to put this geotechnical report together? It's going to be the soil engineer. How would the soil engineer do it? They take soil samples. They do tri-axial testing on it, come up with the allowable soil bearing pressure. This is not going to be our business. This is going to be the soil engineer business. Another 3D picture for the columns, and this is going to be through the pavement again. And look here, here is a pad, right? Understand that this pad is going to be transferring the vertical pressure coming from the column to the pad to the soil. Now the question is, what do we have? These beams. You see these beams running across? This beam, or all of this, these 4 beams, is to control this footing and be sure it's not going to be shifted right or left during the service life of the building. So this beams actually just control the formation and the location of this beam, of this pad. So we don't want it to start to shift right or left. We don't want it to settle more than what we're going to be allowed to settle. So these beams actually are very helpful in foundation design, but we're not going to be working on this beam design. Sometimes we call this also grade beam, or sometimes we call it foundation beam. Both names is going to be okay. Here's a section through the footing. As you see it here, let's zoom in and see what happens. Here's the column, few rebars, you go all the way down with some ties. And as you see here, this is going to be the top of the footing. And you see here, the reinforcing bars of the column is going through the footing. Not just the reinforcing bars, and also the ties or the stirrups. You see here what happened? The stirrups also is running through the column, through the footing itself. So the steel of the column will be running through the pad. It doesn't stop above the pad. No, it runs through it. This to confirm continuity. Now, in the pad itself, we need to put some reinforcing. Now I'm thinking here, the pad pressure is going to be coming from the underside of it, is going to be going upwards. Meaning it's going to be pushing all sides of the footing except for the center of it. Because the center of it, this is what you're going to have, this column, and this column is not going to be going upward. So the footing here is going to start to bend up. And the column is going to be like the support in this case. So someone's going to say, what is supporting what? My understanding, this pad is supporting the column. I understand that. But also, when you look at at this pad design, you need to assume that it has a support, and the support in this case is going to be the column. Here's a section through the footing. As you see here, the reinforcing of the column and the ties are running through the pad. And then here we go, now we have the reinforcing of the footing. Also, look at the reinforcing of the foundation here with this footing. They go in both directions. And the reason is because the type of deformation that happened to the pad and the type of moment that you have on it. So in plan view, you are going to see here a mesh. We call this a mesh. It's going to be reinforcing part in both directions. So if you look here at this footing, there is no top reinforcing. We didn't really add it because we're expecting tension is going to be at the bottom and compression is going to be on the top. I'm going to show you here in a second the estimated deformity shape of the foundation after you apply some loads. In this case here, you see that we have a top mesh and a bottom mesh. So here's a top mesh in different color from the bottom mesh. In many cases, we really need to have this top reinforcing either to control the shrinkage and cracks of the footing when the footing is getting really thick, and also to satisfy the minimum reinforcing required by code in foundation. So the reason that we add this top reinforcing when you have an isolated footing like a pad is because to control the shrinkage and cracks on the top of the foundation is going to be number one, and number two, to provide enough reinforcement to come over the minimum reinforcement needed for the foundation design. Look what happened here. You apply the axial load and then you get some pressure coming from the soil. It's going to be upward. This is the contact pressure that we have been talking about. When this contact pressure is going to be coming upwards, it's going to be pushing this part of the footing up. So actually, if you cut a section right here, you should be able to find out the moment, and it's going to look like a cantilever system. So this looks like a cantilever, right? And the pressure is going to be equal to this axial load divided by the contact area between the footing and the soil. So I simply can say this here axial load is going to be equal to P, and cross-section area of the pad, which means length times width, we're going to say area, which is A equals to L times B. What is L? L is going to be the length of the pad, and B is going to be the width of the pad. Sometimes it's going to be square pad, so L is going to be equal to B. And then this pressure here, you can call it Q. Usually we use Q, the symbol that we use when it comes to soil pressure. It's going to be equal to P times A divided by A. This is going to be the contact pressure. This is a pressure that we'd like to keep within that level soil bearing pressure. Now, this design that I'm talking about here, incising the foundation, actually is going to be an ASD design. I'm going to say ASD design. If you remember, there's two types of designs. We have ASD, a level stress design, and the second one is going to be called strength or ultimate design. So I'm going to say we have two types of designs. And we have load combinations. If you guys recall, we have two sets of load combinations. The other one is going to be called the strength / ultimate. So we have two types of design. When you size the footing, it's going to be ASD design. meaning that this P that is going to be applied to the footing to figure out the size of it is going to be service load. What does it mean by service load? It means that this P is going to be equal to P dead load plus P live load. No load factors. You can say load factor is going to be equal to 1. So when we size the footing, it's going to be ASD design. When you do the member size, which means the thickness, when we do the reinforcing, it's going to be LRFD, which means strength design. Now we're going to have the load factors. So you have here 2 design sets. I want you guys to be sure of this, that you keep remembering this. When you size the footing, which means that you design the soil for the soil pressure, you do ASD design. When you determine the reinforcing bars in the foundation and the footing thickness, is going to be trans design, which means that you're going to have here the factor loads. So in this case, here's the trans design, right? And here's the ASD. Here's the ASD. And for the strength design, what do? We do the common combination. If you guys remember the common combination, combinations. I can type in here. You can say P ultimate equals to 1.4 P dead load, or P ultimate equals 1.2 P dead load plus 1.6 P live load. This is what we do when we do strength design. So what strength design is used for again? I'm going to say strength design is used for, I'm going to say reinforcing, right? And what else? Footing thickness. Okay. So what is ASD design is used for? This is used to come up with the size of the footing. You can say footing size, meaning length and width. And that we're going to be doing here the ASD design. So it's going to be complete 2 different items. The first one that I'm going to be working on is going to be the ASD design, which means the footing size, length and width, and the soil bearing pressure. Second section, we're going to be doing the concrete member design. So as you see here, when this part of the footing is going to start to go up, the tension is going to be at the bottom. And this doesn't happen in one direction only, it happens in 2 directions. So I'm going to say, I'm not clear. What do you mean by happen in 2 directions? I'm going to go back here, 1 slide. I'm going to be looking into this. I'm going to say, if you think about this footing here, the picture that you're looking here at, which side is this? Is this looking this way or looking that way? I'm going to say, if it is going to be looking from here, it means that this section and this section, which is going to be 2 identical sections, right, is going to be the same as this section here. As if you cut a section right here at the face of the column. All right. So this picture here, as if you're looking from this side. You're looking this way. So the section is going to be right and left of the column. But when you look at this side also, if you look from this side, you can draw your section this way, at this face of the column. And this explains that I need a mesh reinforcement at the bottom, because both of these 2 sides is going to be lifting up, is going to be working as a cantilever. So I need to design the reinforcing in both directions. If the length of the footing is the same, like the length is the same as the width, like a square footing, the reinforcing that you put here in both directions is going to be exactly the same. Why? Because this moment at this section is going to be the same as this moment at this section. If you have the same soil pressure, the same cantilever length, you'll end up with the same moment demand. And in a case like this, when you have also the same depth, it means reinforcing is going to be the same in both directions. When you have rectangular footing, you may have different reinforcing at the bottom of the foot. Okay? So I guess this explains here that this lifting up of each side of the footing is going to happen as a cantilever case for the footing in both directions. Here's an actual drawing for some foundation for an actual project that we have done. And actually that was taken in the site. If you see here, you see some soil here, right? And this looks like a table that the carpenter built it in the site. And here's the plan. And as you see here, the contractors start to shade it in pink, and this stripes, you start to do it in black and so forth. So we have some pads here, as you see it there, right? We have more than one pad. And the mark for this footing says F10, 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 F10. So what is F10? F10 is going to be right here. We're going to be looking at the footing schedule. It says here's F10. And the length and width is going to be 10 feet by 10 feet. So we have actually here square footing. The thickness of the footing, which means total thickness, is going to be 24 inches. So, okay. It has top reinforcing and bottom reinforcing. So what do we have in top reinforcing? 4 number 5, 4 number 5. How about the bottom reinforcing? I'm going to say 9 number 7 and 9 number 7. As you see, the bottom reinforcing is the main reinforcement. Top reinforcement is going to be like compression reinforcement. And in lots of cases, in foundation design, in footing design, we ignore the top reinforcing when it comes to contribution to flexural capacity. We just ignore it. We don't consider it to be there. So what is the reason that we have it here? It's just to maintain the minimum reinforcement and control the shrinkage and cranks on the top of the foundation. That's okay. Looks good. So what is this? I'm going to say this is going to be the column schedule. We have this mark C1, C2, and C3. Here's the column size. They're vertical reinforcing the ties on the column. I said, okay. How about here? So if I have F10, I have C1 that goes with it. So, okay. Understand how they're going to look like in actual construction, right? So this gives you the type of plans and drawings that you provide to them. When it comes to detailing, I guess we have a detail here. It says, look at detail 14/S1.4. This gives you the sheet number. This gives you the detail if you like to see how to build this footing. I'm not going to present this here. And instead, I'm going to show an actual picture from the site during construction. Any questions? You're good? Okay, good. Here's the footing. And you see the side of the soil. There is no formwork. I thought it's going to be like straight, like this side, the way it is drawn. But actually, in reality, they don't do it this way. So instead of doing it like 10 feet by 10 feet, they make it like 11 feet by 11 feet. They give you more concrete section. Because your concern here is going to be about the soil and this concrete cover. This concrete cover is supposed to be 3 inches. You see this concrete cover, the distance from this rebar to here. But in reality, this is like 9 inches. They give me like here 9 inches. So I'm good. I have enough cover. So when it comes to the soil contact with the reinforcing, I don't have this problem. And as you see here, you have bottom reinforcing in both directions, right? And then you have top reinforcing. The number 5, and here's going to be the heavy rebars, the number 7. You see here the vertical rebars for the column, they're there. You see here the vertical reinforcing, and it goes through the footing, and then in the footing, they bend it this way. So you have this hook, right? They give me enough hook length. So what they do, they're going to fill this hole with some concrete. They just pour the concrete inside. As you see here, the side is extended. I have some footing wall, right? Wall footing here and some other pads spread in many locations. So, okay, good. So at least now I know how it's going to look like in the site. It's not going to be really actual like box, but you know what? Sometimes if you're going to excavate the entire site, you can do boxes for the formwork because the amount of concrete, you don't want to fill the entire site with concrete, right? But here, because they dug some holes, they start to say, I'm going to give you a little bit more clearance, so you let me do this without a problem. Because what happened if you give me the exact hole size, going to be 10 feet by 10 feet, I'm sure that some of the soil pieces going to be coming or intruding into the footing, and I'm going to be against this because I'm going to tell them, where is the concrete cover? I need at least 3 inches. So this side, just to make it a little bit larger so that we don't complain. As an engineer going there to the site, I'm not going to have any comments. All right, so what is this? Here's the footing after they cast the concrete. And you see here all the ties of the columns, just going through it, right? And the column splice is gonna be right here. You see the column splice? At the beginning, when they did this footing, this column reinforcing is not really to the full height of the floor level. This is only like 4 feet or 5 feet. Picture doesn't show the top of the reinforcing, but this is a fact. You just gave me 4 to 5 feet. Look what happened here. That was the rebar sticking out of the footing first. And then what they do after they cast the concrete footing, and you see now it's gonna be clean. They come here, they do this mark on the concrete pad. This is gonna be for the concrete column formwork. And here's the concrete column reinforcing, right? And you see here, they start to add the vertical reinforcing that go through the column. So this is what you can hear is splice. This is gonna be the splice length from this point to that point. And you see, you have all the ties that I have asked it for. Now they're ready to put the formwork for the column. Here we go. They put the formwork, they cast the concrete column, and here is the reinforcement going to be going through the concrete slab, the elevated concrete slab. Another project. This is actually one of this car wash facilities. And you have the tunnel that you just drive through. And as you see here, this can be like wall footing. And you see the rebars is sticking above. You see how it looks like? Because you're gonna hear concrete block wall, concrete masonry is gonna be coming above it. But look at this. You see here, the cement and the concrete, because this hole was kind of irregular. So they give me more than what I've asked for. I asked here for 2 feet, they give it to me like 3.5 feet. So I said, okay, you're gonna be putting some concrete, extra concrete, and then still filling it back with soil. It's gonna be cheaper for them. But in here, because we're gonna have here some piping and running through here, right? And this is gonna be like a trench. It's gonna be covered with a steel plate, and actually are gonna be driving right in this location. They decided to put here some formwork because we need this concrete surface to be flat. And of course, as you see here, we have some rebars and some steel angles. You see here, you have this steel angle that we're gonna put right here at the edge of the concrete to protect the edge of the concrete later on. And you have lots of pipelines that sticks above, right? You see this, all of these pipelines that go through the footing. It's good for the drainage and the water supply and the whole thing. Another project, which is this. This Sunshine Canyon. I don't know if you guys are aware of it. This is in Santa Clarita up north. And this is what you call here a flare. This flare is to burn the methane gas, you know, because of the smell. This is a landfill, like for the trash, you know. And then they're gonna have big pipeline is gonna bring the methane gas. This height from here to there is about 60 feet. Just imagine how many stories this is. It's made out of steel. And the weight is about 80,000 pounds, the weight of this guy. Supported on one big pad, one big footing. So in this case, I'm gonna call it a pad. This pipe diameter is 4 feet. So just imagine when I stand there, I'm about here, right? So this is really a big pipe. This pipe is not gonna be filled with water. Actually, it's gonna be filled with the methane gas. Methane gas is gonna be sucked through here, and then they're gonna burn from the top here, and you're gonna see the flame coming up. So during the construction, we have this picture that was taken, and here's the pad size. It has top and bottom reinforcing, and because it was extended both ways, the excavation, they decided that they're gonna do here formwork for the footing itself. So actually, when they cast the concrete and they strip the form, the concrete footing was very clean from the sides. It's gonna be unlike this type of construction, you know. It's gonna be unlike this. It's gonna be like this when they strip the formwork. So now let's start the design work. We have no idea about construction, how they build it, and this kind of discussion, right? So, okay. The contact area between the footing and the soil is going to be based on the allowable soiling pressure. We call it here BC, which is the bearing capacity of the soil. What is BC? It's going to be Q allowable. It's going to be allowed bearing capacity of the soil. Where do you bring this? Who's going to give it to you? I'm going to say soil engineer or geotechnical engineer. The contact area, minimum contact area needed between the footing and the soil is going to be determined based on this equation. This says here, A required, the required contact area between the footing and the soil is going to be equal to P, service demand. What's service demand? I'm going to take you here back a few slides to look at the service demand. This is a service demand, which means ASD, dead load plus live load. Just add the loads to each other, no load factors. So it's going to be equal to P service demand, as it says here, service load, as per the IBC load combinations. You need to go to the ASD load combinations and then look at how to add this type of loads, divided by the bearing capacity. My understanding is the applied pressure Q is going to be equal to P divided by A, right? We have done this before. I'm going to go also here, a few slides. I'm going to say this Q, applied pressure, is going to be equal to P vertical load divided by contact area between the soil and the footing. Now let's look here at this equation. It's going to be the same equation, but here we say area required is going to be equal to the P service demand divided by the bearing pressure, which means like Q allowable, right? Same type of equation. I can say here this BC, bearing capacity, is going to be equal to, if you think about this, is going to be equal to the P service demand divided by the area required. When I start here my design, I don't have the area required. This is going to be my unknown. I have the service demand. I have the loads coming to the column, coming to the footing. And I have the allowable bearing pressure from the soils engineer. The question is, how much is this area required? And this is going to be the main equation I'm going to be using to determine the required contact area between the footing and the soil when you have only vertical axial load. So, okay. Example. The column dead load is 850. Live load is 560. You have a square spread footing. It's going to be proposed to support this column. Soil bearing pressure or bearing capacity is 7,000 pounds per square foot, which means 7 KSF. Most economical size of the proposed footing is, can it be 15 by 15? You say, well, I don't know. 12 by 17? I'm going to say no, because this is not square footing. 18 by 18, maybe. 13 by 16, no, it is not. This is not square footing. So it could be one of these two. 15 by 15 or 18 by 18. In many cases, maybe this two footing size is going to be work fine, but the most economical one is going to be the smallest of the two, is going to be satisfying this requirement of the soil bearing capacity. All right, P service demand, just add the dead load to the live load. It's going to be 1410 kips. Required area, the contact area between the soil and the concrete, is going to be equal to the B surface demand, 1410 divided by 7 KSF. So units here becomes now, again, this is going to be, this 7 is going to be 7 KSF, kip per square foot. Here's the contact area needed, 201.43 square feet. Meaning that if you take the square root of this number, it's going to be 14.2 by 14.2. I cannot go smaller. I need to go a little bit larger. I'm not going to do 18 by 18 feet. This is going to be a lot larger, a lot more larger. So I'm going to be using 15 by 15 with a square footage of 225. Now this 225 is larger than 201. So I provided here more contact area between the soil and the footing than needed. Then this is good. So this is going to be my choice. What is the actual soil bearing pressure below the footing? So I'm going to write it here. Let's say actual soil bearing pressure, which is Q. This is not the level, this is the actual. You can say equals. It's going to be equal to 1410 kips, right? Divided by 225. Why 225? Why 225? Because this is going to be the actual footing size. You decide that you're going to make the footing here to be 225. So you cannot really use the 201. That would just be required, but the actual provided was 225. Now, how much is this? Can someone help me here? When you take 1410 divided by 225,
6.27.
How much?
6.27.
I cannot hear you, I'm sorry.
6.27.
Okay, 6.27. Very good, thank you. What units? Anyone knows what units?
Is it pounds per square foot?
Pound per square foot? What did they divide? Did they divide pounds per square foot or did they divide kips per square foot?
Oh, kips.
Okay, KSF. I should compare this to 7 KSF. So this is gonna be less than 7 KSF. What is 7 KSF? This is gonna be the allowed. It's right here, right in the top. So this is good. And this makes sense. When you provide more square footage of the contact area between the pad and the soil, you are gonna be getting less pressure than that level. You can say, okay, yeah, this design makes sense. Then my choice is gonna be 15 by 15. Does it mean that 18 by 18 doesn't work? You can say, no, 18 by 18 is gonna be even safer. But I don't really need it because you're going to be putting lots of concrete that you don't really need. I would just say use 15 by 15. So again, this design here, it is going to be a allowable stress design. This is AC design. And the purpose of this is just to size the footing. And actually what you're doing here, you're designing for the soil pressure. This is not concrete member design. Concrete member design is going to be based on the strength. Let me take you back here to the slide that I put some notes in there. So you have two types again of design, ASD and the trans design. ASD is going to be just to come up with the footing size. And actually what you're doing here, you are designing the soil based on the soil value. But when you design the reinforcing and the footing thickness, you need to do the trends, which means we're going to be doing this factored loads, right? It's okay. Because this is very good, right? I said, okay. How about when the footing supports vertical load and moment? Would I have the same equation? I'm going to say no. I'm not going to have the same equation because I'm going to have an axial load and moment. What should I do about the moment? I'm going to say, if I have an axial load, here's P, the axial load, and here's M, which is the moment applied on the footing. I have the soil pressure here coming from two sources. The first one is going to be coming from the vertical axial load. We're going to call it F, which means stress. Some people call Q. I'm okay with Q or F. It's going to be up to you. You can decide on this. So the stress here on the soil due to the vertical load is going to be equal to P over A. And this is exactly what you have done here. Look at this. The Q or F is going to be equal to P divided by A. Yeah, I understand that. When I have also moment applied on this footing, the stress due to moment is going to be equal to M over S. And we have done this before. We have seen this equation before in mechanics of materials. We have done it here. For the crack section, we have done the same equation. Now, at the end of the day, F12, what does it mean by 1, 2? Let's say the right side, I'm going to call it 1, the left side is 2, or the other way around, doesn't matter. So we can see here the stress below the footing is going to be based on the combined effect of the vertical load and moment. Meaning in one side is going to be F1, the other side is going to be 2. It's going to be P over A, which means F sub P plus or minus F sub M. I'm not sure what does it mean by plus or minus, but we're going to see here in the next slide set. So here is the stress due to vertical load. It's going to be all uniform. And because of the moment, I'm going to have a stress F sub M. This is going to be due to the moment. This pressure here is going to be actually compression of the soil. And you guys, you understand that the soil doesn't take any tension, correct? Soil cannot take tension. If you have a footing here sitting on the soil, you start to take the footing up. Do you think the contact between the soil and the footing is going to give you any resistance? You can say no. Just the weight of the footing and the column. As long as you're going to be able to pull it with some loads, you're just going to lift it up. There is no glue between the soil and the footing, correct? There is nothing there. And the soil is like very fine particles and very loose. So actually, the footing or the soil cannot take this tensile. stress. It can take only the compressor stress. But you know what? Before we decide on this, let's add the stress on the left side of the footing, which means it's going to be F sub P. You subtract here F sub M on that side. So where is side 1? I'm going to say here's side 1. If you like, I can put side 1 to be here. This is going to be side 1. And where's side 2? I'm going to say this is here's going to be side 2. So what do? In side number 1, we add the stress due to the vertical load to the stress due to the moment. Why? Because both of them is going to be in compression. So it's going to be additive. On the left side, which means 0.2, don't forget this is also 0.2 and this is going to be 0.2, right? We're going to subtract, we're going to say F sub P, which means the compressive stress subtracting F sub M. And you're hoping that no tension is going to happen in the soil because we know foundation cannot or soil cannot take any tension. You'd like to have here more compression to stabilize the footing in the entire footing, throughout the entire footing, right? And instead of having loss of tension, loss of moment in the footing, otherwise the footing is going to be lifting up. We don't want this to happen. This explains, if I'm going to go back here a couple of slides, the reason that on one side we're going to be adding the pressure to the vertical load plus or minus the pressure due to moment. So it's going to be F sub P plus or minus. Why plus or minus? It says here 1 and 2 because you're going to have here two sides. One side is going to be additive, the other side is going to be subtractive. Okay, so we have two cases. The first case, if F sub P as a value is going to be greater than F sub M, what's going to happen? If this value here is going to be greater than this value, you're going to end up with trapezoidal distribution of stress. And the entire footing is going to be under compression. This tension will never happen because yours is going to be covered with F sub P because axial load does exist. It's going to be like this, right? So in this case, here's F1 and here's F2. Here you're going to have more compression. Here you're going to have less compression, but you never have tension. Why? Because Fp in value is going to be greater than Fm. What do you mean by this? This value here, let's say 5 KSF, and this value, let's say 3 KSF. So you say 5 minus 3, you're going to end up with 2 compression in one side. The other side is going to be 5 plus 3 is going to be 8. So now I understand that if Fp as a value, numerical value is more than Fm, in this case, I'm going to end up with trapezoidal distribution like this, which is case 2A. This is going to be case A. Like in here, this case A, when F sub P is more than or equal to F sub M, you're going to end up with triangular distribution or trapezoidal. The entire footing is going to be contact with the soil, which is very good. We like this option if it happens. This is going to be our best. I have case B. What happens if you have lots of moment in the footing? So actually the footing is going to start to lift up, which means part of the soil here, right, it's not going to be in direct contact with the footing, even though that it's just right below the footing. Let's see, what do you mean by that? I'm going to say here, F sub M here is greater than F sub P. So in one side is going to be additive, which means 0.1. In the left side, which means 0.2, you're going to take here F sub P, subtracting F sub M, you're going to end up with negative number, which means tension. And soil cannot take tension. So what's going to happen? The foot is going to lift up and no contact is going to happen for a little bit of this footing, right below the footing. Let me show you here. Here's what happened in case B. If the stress due to moment is higher than the stress due to the axial load, the footing is going to start to lift up and then you're going to lose the contact between the footing and the soil, like in this case, right? Like in this case, look what happened here. If you remember this P and E, we went through this in columns. We're going to have the same thing here. This is going to be the force P, and the moment is going to be equal to P times E, right? So actually, what you have is going to be P and M like this. P and M like this. I can take these two forces and split them into just one force, P, and then this E is going to be equal to M divided by P. It's going to be as if you have a vertical load at distance E from the center of the footing. How do I know center of the footing? Because here it says L over 2 and L over 2. Now, if I have this triangular distribution and this distance is going to be X, I understand that the reaction or resultant of this triangular distribution is going to be at 1/3 of this triangular at the base, from the base, right? Meaning if this is going to be equal to x, well, how much is this x? L over 2 minus e. It means total length of this base of this triangle is going to be equal to 3 times x. This is x, this is going to be 3. Why? Because this force here is going to be concentrated at 1/3 of this triangular height, if you like. And this reaction here, it has to be aligned with this force P. I mean, you don't have any other options. Otherwise, this force is going to be unstable. So the reaction is going to be exactly in the same line of action with this force P. I understand that. And this total reaction is going to be equals to P, because summation of the force in the y direction equals 0. So if you have here P, you're going to have a reaction of P. So this reaction is going to be equal to P. Now let me figure out this reaction here in P in terms of x and the stress and this length and the whole thing and the width of the footing. What is the width? Width is going to be perpendicular to the screen, right? The width of the footing in the other direction. I'm going to say, let me see here the equation. The equation says x equals, how much is x? L over 2, 1/2 of the footing, divided length, divided subtracting e. Yeah? L over 2 subtracting e. How about this force P? Can I write an equation for it? Yes, yeah, here's the equation. This P equals to what? This is going to be equal to 3 times x multiplied by what? 3x times the stress F1. What's the stress F1? Oh, this is the stress that you're going to be interested in. You remember the stress value here? It's going to be this stress value. So this stress value times 3x, I'm going to say here, take this divided by 2. Multiplied by B. What is B? B is going to be the width of the footing in the other direction, perpendicular. And this is going to be the total force applied. Let's say, can I take this and try to find out F1 and also replace X with L divided by 2 minus E? I'm going to say yes. And here is the result. This is what you'll get. If you like to rewrite this equation to find out F1, the stress, this is going to be your equation. So, okay, what is this based on? It's going to be based on the vertical load, X distance, and B. What is B? The width, perpendicular to. So if you just take this equation without even replacing X with L divided by 2 minus E, if you just take this equation, F1 is going to be equal to P times, this is going to be this P, right? This divided by 2 times B, right? Just want to be sure that we put it in the right way. So I'm going to say times B. So F1 is going to be equal to P divided by 3x multiplied by 2 and also divided by P by B, which is this equation here. See, great. And just to confirm here the definition of B, right? What is B again? Is going to be this dimension of the footing or the side of the footing perpendicular to the screen, like in this direction here. You can see this is here is going to be B, right? How about E eccentricity? And is equal to M divided by P. Yeah, understand that P times E is going to be equal to M. Yeah, P times E is going to be equal to M. It's correct, makes sense. We have an example. Is a footing exposed to axial load and moment. So the vertical, this surface load, which means it is unfactored, and this is what I need to use when it comes to the footing size. 600 kips, the surface moment, 720 kip-foot, and the moment is giving this direction. Now, when the moment is acting this way, which means this side is giving compression, this side is giving tension. So when you do the section modulus for the contact area between the footing to the soil, we're going to say S is going to be equal to BH squared divided by 6. Very similar to what we have done in uncracked section. B in this case is going to be 10 feet. And H in this case is going to be 12 feet. Why? Because moment is going to be applied this way, right? So this is going to be the depth of the cross-section area or contact area between the soil to the foundation. Just ask about the maximum soil pressure below the footing, which means it's going to be in one side. And then in this example 3 is going to be just a challenge here when you reduce vertical load and what's going to happen. So let's do the first example, which means this one, the soil maximum pressure. In this case here, I have vertical load of 600 kips, moment of 720, length 12 feet. I'm just putting here all the information. The width is going to be 10 feet. Yeah, here is the length and the width of the footing. Contact area between the footing to the soil is going to be equal to L times B, 120 square feet. Section modulus of the contact area is going to be equal to the width times H squared. In this case is going to be L, which is 12 feet, squared divided by 6. It's going to be 240 cubic feet. Now the stress due to axial load is going to be equal to the force, vertical force, divided by the square footage, the contact area. I have here 5 kSF. Due to moment is going to be equal to M over S. Here's the moment 720 and S is going to be the 240. It's going to be 3 kSF. Now here is F1 and F2, the two that we were just talking about. F2 is going to be additive, right? You're going to be adding the two values, and F1 is going to be just subtractive because you're going to have here compression, here is going to be tension. Compression is equal to 5, tension is going to be equal to 3. So it's going to be 5 minus 3 is going to be 2 kSF on this side, and the additive side is going to be all compression. You just take here the 5 plus 3 is going to be 8 kSF. So now I understand that this is a good footing. It doesn't see any uplift, and the footing is safe. No questions? Yes. Yes.
I have 2 questions.
Sure.
First question is, how come this base isn't square? Why is it 12 by 10 and not 12 by 12?
The choice. So the
Okay.
person who designed this footing, he decided that he's going to go here 10 by 12. But I'll tell you the reason why the designer chose it to be this way. But go ahead and ask the second question.
The second question is, I'm not very familiar with the section modulus. So for the exam, would we have it on our cheat sheet?
Are you familiar with the moment of inertia? Do you know the equation for the moment of inertia?
I forget the numbers because there's so many variations.
Do you have an access to your cheat sheet for the first midterm?
Yes.
Okay, can you open it and let me know if the section modulus is there or not?
Oh, okay.
Can be sure. Yeah, go ahead.
Cheat sheets. It is BH squared over 6.
Excellent. All right, so we have it.
Okay. Okay, thank you.
Very good. No problem. Any other questions? All right, now let me answer why this footing is not square footing, right? Why the designer has chosen to be this way? This is going to be a good question, right? So I'm going to say, if you're adding here a foot, let's say you start with this footing to be 10 by 10. So I'm going to say, let me say here that I start with this footing here to be 10 by 10, like a square footing. And I didn't like the numbers, like the soil pressure, because soil pressure is not good, right? It's going to be above the allowed. And I'd like to add a little bit of concrete to it. Should I increase the width or the length? I mean, should I make it like this or increase the width this way? Right, which one?
Increase the length with the column.
Well, if I increase the length of it, look what happened. The contact area is getting increased. So whether you add a foot in this direction or a foot in this direction, you're going to have the same amount of increase in the contact area between the concrete and the soil, correct? Let's say that I started with 10 by 10. I'm gonna make it here 12 by 10. Should I make the 12 in this direction or make the 12 in this direction? You say it doesn't matter because at the end of the day, the contact area is gonna be 10 by 12, which means this number here, right? But look what happened here to the section modulus. It says BL squared. When you increase the length, the S is going to increase a lot. Why? Because it's going to be L squared. Now I want you to think here, compare the change in the S value. When you say 10 times 12 squared versus 12 times 10 squared. Are they the same? Say, no, they're not. So which one is larger? When you put the 12 in the direction of the moment. So if the moment is acting this way, I'd better increase and add an additional concrete in this direction, not in that direction, to save a little bit in the concrete volume at the end of the day. Did I answer the question? All right, good. All right, thank you. So we're going to say in example 3, it says the vertical load has been reduced to 240 kips. How about the moment? Moment is the same. How much was the moment here? 720. And the load is instead of 600, now it becomes 240. So the question is, what's going to happen for the soil below the footing? Okay, let me try this. Here is the vertical load 240. Moment is going to be the same. From the previous example, I know the footing size is going to be 12 by 10. Here is contact area. Here is section modulus, 240. F sub P, which means the vertical force due to the axial load is going to be 2 KSF, and due to moment is going to be 3 KSF. Now we are in trouble because this footing is lifting up. On the right side of it, you're going to have a total of 5 KSF. On the left side, you're going to have -1. And this cannot happen. I mean, soil cannot take tension. So I cannot really say that one side is going to be 5 and the other side is going to be -1. Instead, I need to solve this type of formulation, this equation that they have. It's interesting. It's going to be equal to the 720 divided by the 240 and divided by P to find out this E. E is going to be 3 feet. And X, this distance, if the total length of the footing is going to be 12, 1/2 of it is 6 feet. So we're going to take 6 feet, subtracting 3 is going to be 3 feet. Yeah, this is going to be 6 feet from this point to that point. 1/2 of it is going to be 3, the other half is going to be 3 feet. Just use the equation. The equation says F1 equals. Now look at the stress. The stress is going to be equal to 5.33 KSF if you use this equation. If you decide just to add the values to each other, like if you use here, one side is going to be what? 5, the other side is going to be -1. But -1 would never happen. So the reality is, because this uplift, the stress here is going to increase a little bit, right? From the previously calculated 5 KSF, and that was wrong. I cannot consider this because concrete cannot, concrete to soil cannot take any tension. Now it becomes 5.33 KSF, and this is going to be the right answer. Questions? We're good? All right. What is this combined footing? This is not mat foundation. This is going to be a footing supporting 2 columns. So what happens when you have 2 concrete columns close to each other? The 2 footings are going to be overlapping. So you can just decide to put them as 1 footing if you want to. Like in this case. Distance between the 2 columns just have to be kind of close to each other. So if you like to put 2 separate pads, they're going to be overlapping. So you say, well, why don't I just put it in 1 footing? It's fine. It's going to be 1 concrete member. It has 2 columns on the top of it. We have an example for that. Now I don't have any new equations for the soil, right? It's going to be the same equations I had started with. But when you have here 2 columns, do you think that the column load is going to be the same? Most likely, no. In buildings, most likely when you have a situation like this, the 2 column loads is going to be different. As it says here, we have combined footing supporting C2 and C4, right? A level soil pressure is going to be 8,000 PSF, like 8 KSF. Column spacing is 8 feet. So from the center of the column to center of the column is going to be 8 feet. The column loads are given in this table. Look here, they are not the same. C2 is gonna have less load than C4, right? Dead load on live load. I was gonna say here, okay. The first question, the footing dimensions. What do you mean by the footing dimensions? Which means if you like to solve or to provide a footing for this, what size would you use? This is going to be based on the fact that the soil bearing pressure is going to be given to you, that level, 8,000 PSF, and you have the spacing between the columns, and then you have the column loads. Which one do you think is going to be appropriate design? Should I go with 20 by 20 feet? Does it make sense? I have two columns spaced this way. I'm going to say the footing is going to be like this. Because actually in your design, what you're trying to do here, you're trying to keep this distance from this point to that point, right? This cantilever length on this side to be kind of close to the value of this cantilever length, close to the value of this concrete cantilever length as much as you can. Not exact science. Don't forget that this is not exact science. We're not saying, oh, it has, if this is going to be 5 feet and 4 inches or 0.34, right? This is going to be the same 5 feet, 0.34 is going to be, no, we don't do it this way. We need to come up with some reasonable values to be used in construction. This is not math, right? This is going to be design, engineering. It's different from math. We're not mathematicians. So I'm going to say, would you do this like to be square footing? Would you do here square footing? We're going to say no, because the cantilever length is going to be completely different. So I cannot do something like that. Just imagine if you do something like this, right? Square footing, you just put it this way, right? No, it doesn't make sense. I'd like the long direction to be in this direction here. Why? Because you have the column spacing, you take this cantilever, same as this cantilever, same as this cantilever. So most likely the length of the footing is getting in this way. So I guess 12 by 12 is not good. Maybe 12 by 24, maybe 6 by 24, but not this, not that, right? And then it says the distance from the column C4 to the left end of the footing. What is that? Distance from the column C4, which means this distance here. They say, how much is this? What's your proposed value? Okay. Let me see what I can do about this footing first. Here's column C4 and column C2. Dead load, live load, dead load, live load, added together. On the left side, I have 1250. The right side, I have 1,000 kilos. Supported by one footing. Total force is going to be equal to 2250 kilos. Just add these two values to each other. Total force is going to be right here. If you like to eliminate the moment on this footing here, you'd like to put this resultant force to be right in the middle of this footing. So actually the location of the footing is not determined yet. I can bring it right, can bring it left. So here's a proposal. I propose here to go as 12 by 24. And here's also the solution. This is going to be 8.5, this is going to be 7.5. And the spacing is going to be 8 feet. But we did this kind of design or layout based on the fact that I'd like to bring this P sub T, which means the total force, to be right in the middle of the footing. And this resultant force, when you think about it, if you have here two forces, 1250 and 1,000, right? This gives you here 1250, it's going to be 1,000. The resultant force is going to be shifted a little bit left. Meaning, I need also shift this footing also a little bit left. So that the center of the footing is going to be right at the line of action of the resultant force. So resultant force is going to be right here in plan view, right? And you see this two diagonals, meaning I'm going to put the footing right here in the center. That's going to be aligned with the resultant force. Let me take here 2250 total force divided by 8 KSF. What is 8 KSF? Allowable soil bearing pressure. So the area required or needed is going to be 281. I have some proposed answers, right? So I'm going to try maybe 12 by 24. Would 12 by 24 work? I say yes, 12 by 24 is going to be good. I mean, you can check it out yourself. You say, here's the provided area. It's going to be 288. Section modulus is going to be equal to this much. Let's just take this force 2250 divided by 288. How much is that? Can someone help me? Because what I needed here is 281. So I decided to provide 288. What is Q, the actual Q? Yes. Yes, how much is that?
4.34.
How much?
4.34.
5.34? How's that?
4.
Okay, it's my mistake. Does it make sense now? 2250 should be the total force, right? How much is that in terms of KSF?
7.81.
7.81.
81.
All right, good. KSF. Close to 8. So that's not bad. But now I'm concerned about any additional moment. But you know what? If you put the resultant right in the center of the footing, you don't have any moment. Because when you look at the soil pressure coming from the other side of the footing, you're going to have uniform pressure, right? The resultant is going to be right in the center of the footing. If you made this 8 feet, 8 feet, 8 feet, you're going to end up with 24. But in this case, you're going to have some eccentricity. Because the resultant, right, is not going to be aligned with the center of the footing. So, okay, here's the section modulus, right? Because if you're going to have a minimum, it's going to be applied in this direction for any eccentricity. But let's see first the eccentricity. Here's the foundation or the footing elevation, and this is a plan, right? The first force at C4 is going to be 1250. The second force at C2 is going to be 1000 kip. Distance is going to be 8 feet. Here's the location of the resultant force. Total force is going to be 2250. If you do your analysis here to find out this location, right? I'm going to call it here X1. How do you do X1 here? You take the moment about this C4. You say 2250 times X1, right? It's going to be equal to 1000 times 8 feet. Yeah. So with that, you should be able to find out X1. And X1 is going to be equal to 3.55. So this distance here is going to be 3.55. When it comes to construction, and someone's going to say 3.55 feet to you, you're going to say, why don't you make it 3.5 feet? Let's just make it 3 feet 6 inches. It's going to be much easier for us to understand. This is what anyone is going to tell you here. Does it make sense? Yes? No? I'm going to make it here 3.6. So I'm going to make this to be actually in reality, this is going to be 3.5 feet, 8.5, 7.5. So now this C1 is going to be 8.5 feet. If this is going to be 3.5, this is going to be 8.5. Now, if the resultant force is going to be aligned with the center of the footing, it means we don't have eccentricity. And the stress is going to be equal to 7.8. How did I come up with this stress? It's going to be equal to 2250 divided by the total square footage of the contact area, means 24 by 12, which is this 288. But I'm going to still have a little bit of eccentricity. Why is that? I'm going to say because if you put it exactly at 3.55, you wouldn't have any eccentricity at all. It's going to be zero eccentricity. I'm going to say you have very small eccentricity. How much is this? It's going to be 0.05 foot. This is going to be your E, right? It's going to be 0.05, 0.055. It's going to be very small. So actually, this footing is exposed to a little bit of a moment. And this moment is going to be equal to 2250 multiplied by 0.00, 0.05, let's say. It's going to be very small eccentricity. So we're going to say, let me try this. Here's the moment. And the moment, when you look at the value here, is kind of large, right? 123 foot. It's not small. And M over S in this case is going to be 0.1 kSat. So here's the good thing. When you try this equation for the stress coming from the vertical pressure and the moment, look at what happened. One side is going to be 7.1, the other one is going to be 7.7, and both of them is going to be less than 8. Design is still okay. In some cases, if your numbers doesn't work, right, and one of these two values is going above 8, it means that your choice was incorrect, and maybe you need to make the footing larger, or maybe you need to move this left side, maybe you need to move it a little bit to the right, or so forth. Any questions in this combined footing analysis and the idea behind it?
Just wanted to check. So basically, we first easily determine the size of the footing, and then
Yeah.
once we do that, then we center the columns we center the footing to the columns.
We don't center the footing to the column, but we center the footing to the resultant force.
Okay.
Yeah, because if you just say to the column, it means this is gonna be here 4 feet, right? It's gonna be 4, 4, it's gonna be 8 and 8. But to eliminate the eccentricity, I shifted this footing a little bit to the left. So I moved the entire footing to the left, right? I moved it this way a little bit. Why? Because I have here heavier load than this load.
And then how come when we design for beams, we have a fee factor, but for footings, we don't have one?
Yeah, okay. Were you here when I started my discussion about this? Very good question. About this design methodologies.
Oh, okay. Sorry, I missed that.
When you do, yeah, when you do ASD design, just to come up with the footing size, which means length and width, you just say P dead load plus P life load, there is no fee factor. If you like to design here for the trends or ultimate design, you're going to do factored loads. And in this case, you're going to have the fee factor. This when you design the concrete member itself. Okay. Make sense or no?
Yes, thank you.
Okay, no problem. Now I'm going to stop at this point and show you quick the homework. I'm just trying here to help. I don't want you guys to think a lot about it. It's very simple. About column design, you guys remember this interaction diagram? You say, yeah, this is the same one that we have in our slide set. It says here, this is going to be given for this column information. I understand that. The column supports 7 stories and roof. Tributary area 600 feet. Okay. Roof dead load. Roof, right? When the roof dead load is 120, dead load count from the roof is going to be 120 PSF. Multiply by 600. Divide this by 1,000. It's going to give you here the roof, axial vertical load on the column. And then again, the roof life load, you do the same thing. And then you do the floor, and then you do the floor. Now, this floor life load and dead load multiplied by 7. Why? Because you have 7 stories and then 1 roof. Okay. It says here, determine the design service load and design ultimate load, and says show analysis. So in here, you need to show me how did you come up with these 2 values, right? Define the load on the column. It's going to be ultimate and service, which means I need total dead load, total life load, separate from the ultimate 1.4 times P dead load versus 1.2 dead load plus 1.6 life load. Advice if the column can support the ultimate load demand above. No analysis is needed. So what do you mean by no analysis is needed? It just says indicate and mark the chart. So let's say you come up with the axial load or vertical load and say it's going to be this much. Let's say it's going to be 1,000 just for sake of discussion, or 900. Doesn't have any moment that goes with it. So what I want you to do is just to come here and then draw a circle. You say, this is going to be my load, right? And this is going to be for number what? You can do it in the PDF, you can print it, mark on it, it's going to be up to you. And you just say, without any analysis, this column is going to be okay, and this is going to be problem number 2. You say here, problem number 2. To give you the answer to problem number 2. You're done. Column is going to be okay. So whenever it says here, no analysis is needed, you don't do any analysis, just mark the chart. It says when the moment equal to 600 kips and P is going to be equal to 900 kips compression. Is this okay? Is this column okay? Let me check. M is going to be 800 kips. Where's M? No, M is 600 kips. Sorry. Here is 600 kips. Gonna come here, draw a line. How about the axial load? 900 kips. Is this column okay with this 2 load combination? Can someone help me?
No.
No, because it's gonna be right here. This is not good. This combination is going to be right here. You say column is not okay, and then you mark it in place. So whenever it says no analysis is needed, you don't do analysis, you just mark the chart. And I want you to do this, and be sure that you do it correctly, because you're going to see something very similar to this in your exam. Certain points, I'm going to ask you to determine it and show analysis. Other points, I'm going to say no analysis is needed. Just mark this point. I've seen it before that I write all of that and I make it in bold, underline it, and I make it in uppercase, the whole thing. And then I see someone is trying to solve for this point, right? He's trying to say eccentricity is going to be this much and spend the time. So be sure that you don't do this. Okay. This lecture is recorded. I'm going to post it once I'm done. So be sure that before you start to do this, be sure that either that you remember exactly what I have said, or you just watch this lecture before you start the analysis. All right, guys, any questions before I leave you? I'll let you go.